I'm going to talk you through Mr. Smith's prototype incline plane apparatus. You can see from this side view that it's two pieces of straight material with a hinge at the junction point, so it enables it to move between 0 and 90 degrees while still keeping the same arrangement. There's a protractor here, so you can measure reasonably accurately the angle. This lab jack here can be used to fine-tune the gradient to get the required reading of the protractor. Up here we've got a Newton meter, so this is measuring the force parallel to the plane. And here we've got a small balance which is fixed onto the plane, so this is measuring the force normal to the plane. And here we've got a weight loaded onto the Newton meter, and it's seated in a little sort of carriage, if you like, that I've made from Lego here, and that's just so that we can minimise as much as possible the effects of friction on the surface. It just enables the weight to move in that sort of plane as we change the angle of the plane. So if I pick up the camera so I can give you a better view here. So you can see down here the hinge at the junction point. We've got the protractor, so we can take the reading of the angle of the plane. There's the lab jack, and then here we've got the Newton meter hanging off a bracket, a mast hanger, and the balance there. So if we have a look at some readings, at the moment we've got the plane set at an angle of 45 degrees. Hopefully you can see that reasonably clearly with the red line on the back there. You can see the reading on the Newton meter. That's about 3.5 newtons of force parallel to the plane. And down here, if we look at the reading on the balance, you've got approximately 350 grams, and that's at right angles to the plane. I'll move this back over here. I can do an adjustment to the angle, so I use oops, if I get out of the way, you can see as I rotate this, it's changing the height of this sort of concertina mechanism of the lab jack, so it's changing the angle of the plane. Hopefully you can see that as I do it. Just going to lower it down. So what's happening now is we're changing, although we haven't changed the amount of mass in that situation, the components of the force are being registered differently. So as I lower the plane, there's going to be a bigger component of force acting on the balance than there is on the Newton meter. So if I adjust this to approximately 37 degrees. So this is the plane adjusted now, so I've lowered it slightly. If we zoom in again so we can take the measurements. Okay, so we've got the plane at about 37 degrees. We come up to balance. can see that's now at just under 400 grams, and the Newton meter is reading almost exactly 3 newtons. So the components of the force have changed with the change of the incline. To show you the extremes, this plane is obviously adjustable between 0 and 90. Try to take the weight off it here, just get the clamp out of the way. You can see I could manually adjust it to whatever angle I wanted. If I take it up to the vertical, which I won't do because things will probably start dropping off, but if I take it a reasonable way, I'll give you an idea. You can see that the components of the force are shifting so that the majority of the weight is going to be read through the Newton meter, and very little of the weight is going to be registered by the balance. In fact, when I get it to the vertical, there'll be no component of the force acting in this way, so the balance should read 0. And when I get it to the vertical, component of the force from the Newton meter will be the full weight of what's hanging on there, which is 500 grams. If I lower it down this way, release this so that my little wagon doesn't fall off. You can see that now all the force is acting vertically down, and so it's completely registered by the balance. The balance is reading slightly below 500 grams, and obviously the Newton meter, now it's relaxed, is reading 0. You've got no force acting in the horizontal plane anymore, all of the force acting in the vertical plane. Thank you.